maxima and minima. When a problem asks you to take a derivative, you're going to have to find a max or a min. Taking derivatives is a basic concept in math, and, of course, optimization.
I'm not interested in the concepts of math. I just want to know how they solve the problem.
You're an idiot if you think you can figure out how they solve the problem without a basic understanding of math. But don't take my word for it. How about a trip to the kitchen?
You're joking, right?
Do you want to know how they solve the problem or not?
Just put this on your head.
Step right up. There you go. Now we just pull this down all safe and snug. Alright, make yourself comfortable. There we go. And when you're ready to travel to the kitchen, just say the mathematical words.
No!
That'll suffice.
Bon voyage!
Shalom. I personally prefer to take the scenic route. Welcome to the kitchen, man of lesser beard.
Hardy har har. What was with the cap?
Oh, that was just for fun.
What?
Oh, nothing.
So this is an optimization problem?
Yes.
So there's this jogger guy, and he finishes running the park, so he has to get back to his home, to this kitchen apparently. And so we need to find the minimum time?
No. We need to find the point along the street that will give us the minimum time. You see, the jogger has to run across the park and onto the street so he can bike the rest of the way home. What we're looking for is a good point along the street for him to rejoin it at.
So we can start by drawing a right triangle, unless we don't need to draw a right triangle.
Well, actually we do, but not quite in the way you were probably thinking. Now, to start off, we should draw a dotted line to represent the distance across the park, between the jogger's starting position and the edge of the street. Next, we draw a solid, perpendicular line to represent the street that the jogger's house is on. There we go. Now, in order to solve the problem, the mathemagicians needed to know a few things, like the distance from the jogger's starting position to the street. 8 yards. The distance from the edge of the park to the jogger's house down the street. 15 yards. The speed at which the jogger can run through the park. 3 yards per minute. And finally, the speed at which the jogger can bike down the street once he reaches it. 5 yards per minute.
Okay, so then how do we come up with an equation that gives us the time?
You're kidding, right?
Really? Could you be any more condescending?
Of course. Like this. You see, there's a very novel and little-known method a mathematician uses to find the time in this situation. You ready?
Yeah?
The hypotenuse.
So this represents the distance the jogger traveled across the park?
Very good. You're being one-upped, Mr. Streets.
Okay, but I don't see how that helps us find time. Besides, you said that this had nothing to do with time.
I said that minimum time wasn't what we're trying to find. What we're trying to find is the point at which the minimum time occurs. And for that, we need an equation. But first, let's label the point that gives us the minimum time. The intersection between the hypotenuse and the street. X. Now, consider that speed is just distance over time. That means that time is just distance over speed. That means that the distance that the jogger runs across the park, the hypotenuse, can be found using Pythagoras. And, well, the other distance? That's just 15 minus x. Now, if you put these each over their respective speeds, that gives us the times it takes for the jogger to move over each of these surfaces. And if you just combine the two times, you get the total time. Total time equals 15 minus x over 5 plus the square root of 64 plus x squared over 3.
But then how do we get the x value of the minimum out of that?
Simple. We take a derivative. Now, behold, the magic of derivatives. Little trick I learned over in Toronto. And there you go. A bit of a complicated piece, but nothing you couldn't handle, I'm sure. Now, once we have the derivative, all we have to do is set it equal to 0 and move the constant over to the other side, like so. Then a little cross-multiplying gives us this piece, which we can just solve for x. It requires a little bit of work, nothing too fancy, honestly. And finally, voila, the answer. Plus or minus 6. Now, we have to keep in mind we have a domain. You see, the distance can't be less or more than the distance of the street itself. So the negative is out because we can't have the negative distance. I mean, obviously. So then now all that's left to do is to make sure our answer actually is a minimum by using the first derivative test. And as we can see, it changes from positive to negative at 6. So our answer is 6 yards. So it all works out. He should rejoin the street at exactly 6 yards down, which is exactly where the mathemagicians directed him to go. That should get him home in about 3.8 minutes, or 3 minutes and 48 seconds, exactly as long as they predicted it would take.
Whoa, hold on a second, that's it? So what was the deal with the teleporting boxes in the refrigerator? How'd you do it?
Oh, right, that was just me messing with you. Now, as to how, you see, my friend, sufficiently advanced mathematics is indistinguishable from magic.